December 2019. John Foster, Gerard Collins and I, Liam Edwards, ventured over from our side office at the old Footscray Flower Market to the banks of the Moonee Pond Creek, where we were to meet then project engineer Ryan Eade to figure out how to install 8 girders over this little creek. An easy task, you might think. Just 8 out of the hundreds of girders for the east zone of the Westgate Tunnel project. But this location was anything but ordinary. We arrived at a shallow creek, 40 metres wide, fluctuating with the tide. Long grass covered the banks and our boots sank into the mud as we trudged along, dismissing idea after idea and discovering all the more constraints. Above us, high voltage power lines hang 45 metres above the ground on the west bank and much lower on the east bank. Ryan informed us that the utilities team were already removing the lines on the east bank as part of the project. Great, one constraint down. John suggested lifting off the Dynon Road Bridge, but that idea was quickly discarded when we realised that we needed an NHVR permit just to roll a mobile crane over it at 12 tonne per axle, hence it lacked the structural integrity required. Okay, so what about the east bank adjacent the CityLink off-ramp? Well, that road there provides access to the Metro train stabling yard and could not be closed for more than 8 hours at a time, so no setting a crane up there. And then there's the off-ramp itself, which we'll later need to work up to the millimetre against. What about a barge? Gerard suggested optimistically, but that was also a no-go. The creek itself was barely a metre deep at full tide, and the creek bed was more flexible than the intended completion date of the Westgate Tunnel project. The geology of the area was really challenging, so it's river sediments underlined by crude island silt and Fisherman's Bend silt. Now, to put this in layman's terms, when 400mm by 400mm square piles were driven into the bank, they were disappearing quicker than they could be hammered. So, with areas here on both sides of the bridge taken up by the abutments for the bridge, we were left with only the east bank as a feasible location for the crane. But it wouldn't be easy, as this east bank also shared a shared user path, which would later need to be diverted across the creek prior to the crane pad and back over the creek later on. Just another challenge that we had to work with. Now, dare I say that every crane in the country was considered for this lift. Tracked machines would have allowed some manoeuvrability between lifts in this tight area, but designing a piled platform for track loads of a crawler crane of 750 tonne and above with superlift was just not proving to be feasible. So we started to look towards outrigger cranes with superlift, and that's when we looked at the LG 1750. We learnt that the SX models of the LG, designed for wind turbine construction, had an adjustable 15 to 20 metre tail swing, but less capacity than the older SL models. The SL model, stronger on short boom lengths, could accommodate a 13 to 18 metre superlift tail swing adjustment, and this was just what we needed to clear the CityLink off-ramp but still get the capacity required for the install of each lift. So Gerard and I set about determining the ideal crane position, considering all the constraints and checking the superlift requirements for each lift to ensure we wouldn't run into any issues down the track. The position was locked in, and the geotechs at FSG designed a piled crane pad with piles up to 20 metres deep to reach the underlying rock. Essentially, the piles only relied on friction and were purely there to disperse the loads all the way down to the rock rather than rely on any of the surrounding soil, a concept not commonly seen in geotechnics. But before building the piled foundations, we needed a hard stand. We needed to encompass an area from the creek and protect it. And hence a solution was devised where the bank was cleared and extended about 15 metres into the creek with a sheet pile wall encompassing the hard stand. Now, this just wasn't any sheet pile wall. This was an extremely long sheet pile wall, but it was tied back with all these black lines, which are tie bars underground, back to more sheet piles on the roadside to provide that integrity and prevent the wall moving. That's how bad this soil was. And then the wall was monitored every shift by surveyors to check for that movement and make sure that the tidal fluctuations weren't imposing on it. And you can see that platform there fully constructed with the outrigger pads. Now you might have noticed a small crawler crane also pictured on the design drawings. That was for the substructure works, and it was just a 400-ton crane on main boom. We were able to actually encompass that in the hard stand, in the piled foundation design as well. And then those outrigger pads were extended to the height of the LG afterwards, which you can see right there. By mid-2020, the setup was ready to go. The crane was procured, and we all know how 2020 panned out. The project itself was significantly delayed. I myself moved across to BMS Heavy Cranes, and 2 years later, in 2022, we were finally able to begin our 18-month scope on the project with HC26, our SL model LG 1750. In July 23, 4.5 years after initially scoping out the works, we began to mobilise the LG 1750 to Bridge 80 to perform these lifts. The mobilisation itself was the first challenge of execution. First of all, we gained an unregistered vehicle permit for the carrier to drive between its location at Footscray Road over to Dynon Road. Every component had to be loaded and delivered in perfect sequence, as there was no room for stockpiling components at the worksite. The low clearance of 4.1 metres from an overhanging crosshead at the entry to site posed just another constraint. No trucks could have tall stacks, and some of the bigger boom pieces had to come through on low loaders. Now, the heights of the crane pad posed significant challenges. So the crane pad itself, the hard stand, sat about 1.5 metres lower than the adjacent road. And the sheet piles encompassing that hard stand couldn't handle any additional material being added. With the superlift tray needing to slew over the road, we had to consider both the available stroke in the rams of the outriggers and the rams of the superlift tray to ensure that all heights were manageable. So this resulted in pile caps that were 1.2 metres higher than the hard stand, and that posed a challenge for positioning the crane. First step, we begged the Gerotex for any additional material, and we were allowed another 250 millimetres, which is what you see here. And I can go back and show you there, that's that additional 250 mil. And then we used our 300 mil thick OEM crane mats, our steel bog mats that the crane usually puts its outriggers on, to gain that additional height and just get the outrigger floats over the top of the concrete plinths. Now, the only way that we were going to get the crane built was with the help of Premier's LTM 1450, set up in the only position available on the MTM access road, so hence outriggers had to be brought in at the end of each shift. So the 450 was used to build the LG in the full 70 metres of SLDB, and we were soon ready to lift. Over the next month, we pre-spliced and installed 8 full girders, requiring absolute precision from all involved, particularly the surveyors. So each girder had an A girder and a B girder, and they had to be spliced together on stools. The stools had to be positioned so that each segment landed in the perfect location, ensuring the combined centre of gravity was exactly where it was planned to be for the install lift, because we were pre-aligning the superlift tray to that centre of gravity. So as you can see here, this is girder 3, which was the very first install of the bridge. We landed girder at the A girder at 49 odd metres radius with the superlift tray. We then went and got the B girder. That B girder didn't need the superlift tray for install, but what we actually did was used it as a dummy weight to pick up the superlift tray and relocate that tray into the position in line with the combined COG of the girder, ready for the install, which was a small efficiency, but we really needed it on a tight site like this. Now, once that girder was fully spliced, we then picked that girder and slewed it out into position. Now, the installation sequence on this bridge and all the other bridges we did on the project was not in our favour. Due to the temporary bracing procedure, we couldn't work from the furthest girder back towards the crane, meaning that tagline control and consideration was critical. Now you can see here we've got the first segment of girder 8 getting offloaded. Girder 8 is the focus of our Lift of the Year submission, as it was considered the critical lift, and you'll see why in just a moment. So first of all, the A girder was offloaded, and then the B girder was spliced to it, and that tray was relocated, as I explained earlier. And then this is the movement that was required to get that girder into the install position. And I'm going to run you through the intricacies of the superlift tray and why we had to lift the girder and slew it at this 30.4 metre radius. So first of all, we're picking this girder at 31.8 metres radius, and we have the superlift tray starting right in at 13 metres because we always want to start that as close to the crane as possible. Now, it was determined for this lift that 327 tonne superlift tray weight was the ideal weight, and you'll see why shortly. So the first issue though was that using this weight, which was required for install, meant that the tray raised very late, and that's what this screenshot's actually showing. So our total weight was actually, our total hoisted load was 148.9 tonne. But what we first simulate is, when is the tray going to rise? When's it going to pop? And that's what we did for every lift on this project, because we all know that using superlift, it's critical that the tray rises before the load so that the operator can gain their free slew and account for any intricacies in adjustment to that COG that were not spot on in the pre-planning. Now, on this occasion, it was actually one of the latest tray rises on the project. So the tray, as you can see here, our actual weight equaled our max weight when we had 139.5 tonne out of the 148.9. So we only had 10 tonne left up our sleeve when that tray was going to rise. But that was okay. So we got through that, and then you can see there we've got the total load of 148.9, and our tray is clearly off the ground. We then needed to slew this girder about 180 degrees to get it into the install position. Now, this slew meant that we had to clear CityLink, and that's what this small clip here is showing, and that's this passing here. So that's where the tray sucked all the way in. And you can see though that we weren't able to jib this girder up any more than the 30.4 metre radius, or that tray would have wanted to touch on the ground. So ideally we would have had less weight on the tray there, but the reason we couldn't is because of the install, which you can see here at 46 metres. We've then telescoped the tray all the way out to 18 metres radius, and we're now just above our minimum superlift weight because we've jibbed down to 46 metres install radius. Now, as the crane runs 12.5 tonne counterweight biscuits, we could have run with 314.5 tonne, but as you can see, that would have been right above the minimum. The crane would have been fully on its toes, and if we needed any extra radius or anything, we would have been right up there on that F1 utilisation. So we needed to avoid that, and our experience on the previous lifts led us to run with this decision of having the tray pop a bit later, but ensuring we had that extra returning moment when we needed it for the install lift. And you can see there that once the beam was landed, we come down on the weight, the tray touches back on the ground at 13 metres radius, and we've only got the weight of the hook block and rigging. So altogether, we were at 148.9 tonne total hoisted load for this lift at 46 metres radius. Didn't exceed 85% utilisation at the install radius, so comfortably able to stay under CPB's requirement of 90% utilisation on this lift. Now, I do need to give commendation to the CPBJH surveying and methods teams for their works on these lifts. They were imperative to the success of these lifts, particularly for their work in the planning phase, but as well as execution, lining up the COGs and the superlift tray. But we worked with them doing full 3D modelling of the CityLink off-ramp to check both the superlift tray clearance, but also the LTM 1450 of Premier's during setup, that it would be able to pass its counterweight stack underneath. And you can see here, this is the digital modelling of the LG 1750 tray up against CityLink there, the clearance to the pendants checked at worst case. And then you can see here, this is when we did the dry run after the crane was set up, just to check that we could get past, and that's with the tray at the needed 15 meters radius to get the capacity. So that was really good, and we all slept a bit easier that night when we seen that tray cleared as intended. You can see here, there's that tray fully loaded during one of the installs of the first span, where it had to land on the road, and of course we can't shut that road for more than 8 hours, so we had to land it on a Zobies, clear it up before the end of the night shift. Now, it would be remiss of me to not touch on the rigging details meticulously curated by Jared Collins for not just this lift, but every lift on this mega project. The rigging concept was first developed back in 2019 and refined in the lead up to the first girders arriving on the project. And whilst the sink hoist and triangle conception was actually a recent hot debate on LinkedIn, I believe that recognition goes to John Foster, Malcolm Smith, Lachlan McRae, and Jared Collins, amongst others, for the overall arrangement. Jared's work in planning each lift on the project involved working with the CPBJH temp works teams to calculate the required sling length of each leg at both the pick and place. And then he determined the overall combination of slings and sink hoist stroke to safely pick the load level and then adjust both the incline and camber of the girder for the install. Now, whilst the original concept actually included 4 sink hoists, it was suggested that only 2 and a triangle would have the same effect, and this was proven true in small-scale testing prior to being put into action. And of course, the axial load and the tension and the angles in each leg was all checked against the allowable prior to the lift going ahead. Now guys, this story ends here, but for the crews, it was simply on to the next span, where they would lift the longest girders of the project at 82 meters length and 251 tonne total load. Some key personnel here. This is not everyone, but there was a number of people involved in getting this lift off the ground who should be mentioned. And these are some key contractors who were involved with making the lift happen. Thank you very much for listening and for considering this application for Lift of the Year 2024 over 20 tonne. I really appreciate your time. Thank you very much.